Does the unconscious mind even exist? Does it? It's a good question. How do you define it? How would you know? Right? So it's very difficult to know. How about, well, most of you guys who just took my class ought to know some insights into the unconscious mind, particularly in the context of memory. We know it's present at one level or another, right? Because we can see forms of implicit memory evident in patients like HM, right? So that could be an answer. But, so you're all now your own scientists in your own laboratory, and you'd like to set off on an endeavor to test certain ideas and measure certain things about how certain cognitive operations and processes are happening. What are some questions that you might be interested in addressing? Anything sound cool? What would be something you'd be interested in studying? A question of cognition or physiology or memory?
What initiates the addiction centers in the brain? Does everybody get initiated the same way?
Okay, so what initiates the addiction centers of the brain, and are people initiated in the same way? That's one way to start. Okay, so a lot of the models that people have about, say, neurobiology of addiction, for example, has to do with associative memory. You associate a certain stimulus or a certain place with a stimulus that you're expecting a certain response in, right? You can have context-dependent responses to certain drugs, for example. So a certain amount of heroin in a crack house that a person's used to booting up in is not going to give them as much of an effect. They need to boot up more and more and more, which is why people end up dying, because then they go to a different contextual location, a different neighborhood, a different house, and they think they need that same amount to get the same high. But they don't, because it's context specific. And so they take that same amount that would otherwise kill them, and indeed it does sometimes. So we have to, basically there's an underlying neurobiological element of memory sort of serving as a core component to that sort of model, which is the ability to learn and remember the associations between different stimuli and different contexts. So, any of you guys from last quarter remember what we talked about with the medial, as a model of the medial temporal lobe that's built to, or that is thought to operate in service of our ability to learn and remember the bound associations between items and context? What do we talk about? Well, I had like most of you guys together like 2 weeks ago. We just finished talking about this. Yeah, so the hippocampus is a really important structure for this. So it's so important that if we were to make a hierarchy of it, we might put it on the top of the pyramid. Okay? So you might have something up top here that is our, let's marker 6. It might be the hippocampus. Now, the idea is that we can think about one of the roles of the hippocampus being to bind the associations between items and context. Okay? So, maybe this is kicking off some of the dust and rust for you guys, but we call this the what model? BIC, exactly, yeah. Because we can't think of a better name, it works perfect. BIC, right? Binding items in context. Okay, now the way that this can be developed as a framework then that we can build from, okay? So now we know that we have different pieces of information. We have the information of an item, and we also have the information of a context, right? So an item might be like, oh, that person seems so familiar. Where do I know them from? You remember the item, right? But, oh, man, I don't know where I know them from. You don't know the context from which you experienced that episode in the past. Okay, so different pieces of information. So we can model that as different pieces of information that get fed in to the hippocampus. So you might have information of items and information of context. Okay? Any of you guys kick off any of the dust and rust from spring break and remember the names of these brain areas that we thought were involved in supporting these different types of information flow? Yes?
Is the amygdala related to context?
Not quite. The amygdala is not quite the structure we talked about being related to context. One sounds really similar to this. Parahippocampus. Okay, so that's one different structure, and that was involved in supporting processing of context. So parahippocampus. Okay, this is doing context. Now, the item processing was coming through what we call the perirhinal cortex. Okay, so what you might think of as information of what versus information of where. You guys feel pretty comfortable with this framework that we're building? Okay. So, what and items, this can kind of, as we talked about a minute ago, we can experience that as when we remember things that are familiar. Yeah? Everybody on board? So that can be kind of what we consider familiarity. Okay? Now, on the other hand, we talked about you can recollect the clear details. No longer it's just that, oh man, that person seems so familiar, where do I know them from? Now it's like, oh, I know exactly who that person is. I know where I know them from. I know the kind of car they drive. I know exactly the rich tapestry of information that weaves together our memories from the past. Okay? So we can compare and contrast recollection and familiarity. What this model is helping us to do as we build it, okay, is it's allowing us to start building some frameworks by which to create some experiments and to ask some experimental questions about hypotheses. Okay? So, the first question we can ask is, are these even different processes, recollection versus familiarity? Okay? So remember, recollection is kind of that binding in context of the items together with the context that they were experiencing. Now, when we do that, we can ask, is that a separate phenomenon than familiarity? Well, if I asked you that question in a laboratory, how could you test that? Yeah, okay, that's a really good start. Brain imaging. That's one way you could test it. Well, that's one method you could use to test it. How about, let's take that to the next step forward. Beyond the method, what would you do in brain imaging? Let's go to that next level of thinking critically, of designing experiments. What could you do using brain imaging to test if recollection and familiarity are the same or different? Yes?
You give them a task.
for instance, well, connecting them to some sort of imaging testing, and then we give them a task to see if there's a difference between when they're familiar with something as opposed to when they recollect something.
Yeah, so you can give them different tasks to do. Okay. So one thing that you might do is you might give them different tasks to remember items or to remember context, right? And what your hypothesis might be in a neuroimaging study would be what? Yeah. If the question is fundamentally, are these even the same brain processes or the same cognitive processes, we might be able to gain insight into understanding that by seeing, do these two different types of information, memory for these different types of information, do they activate different brain areas? If so, it might suggest that they're fundamentally different, right? But what if they activate the same area? Ah, yeah, so it could activate the same area, but what if it activates the same area in different ways at different times? That could also suggest distinctiveness, right? And so we can use these tools, like you accurately said, brain imaging, ERPs, fMRI, to start to understand these questions of psychology, you know? Because it could be that these are the same process, just one's a strong version of the memory and one's a weak version of the memory. Fundamentally the same memory, right? But it could also be that they're very different types of memory. Imaging gives us one tool by which to do that. What other tools could we use? As an approach. How about if, instead of seeing what areas in the brain light up with imaging in healthy, normal people, right? Let's say everybody likes fMRI, for example, or seeing what types of patterns are evident on the scalp with EEG. What if instead we asked about what happens if you chop areas out? It's another way to ask it experimentally, right? To test hypotheses. Because what if you have patients who have damage to certain areas of the brain, and they lose the ability to do one of these types of memory, but they're totally fine in another? That's pretty compelling evidence, wouldn't you say? But what if you have patients that have damage to a certain area, and both processes seem to show impairments, and they come down? It suggests maybe the opposite interpretation, right? Now, would any of these singular approaches be the gold standard, the holy grail, upon which you could hang your hat scientifically and say, done. Drop the mic. I solved it. We're going home. No. What we would want to do is have what's called convergent validity, the convergence of different viewpoints on the same question and problem, showing similar patterns of results. That gives us a lot more confidence to drop the mic, right? Because we already talked about how our intuition is often wrong, or it can be, right? That's why we try to use the scientific method to help keep us in check. And so, if that's the case, then we want to make sure that our scientific findings, that we don't use that we don't make a broad generalization based on one finding. We want to use different methods and different approaches that can help us to draw stronger conclusions. Which is why I try to structure this class into having your lab reports represent the convergence of several different analyses that you do to answer several different types of hypotheses within the data. So that at the end, you can write about in your discussion sections how a convergence of evidence might lead you to draw a certain conclusion or interpretation. Make sense? So we kind of build into that. So we're going to talk a lot about recollection, familiarity, and these different types of memory processes, because that's the kind of data that we have. And in fact, I'm even going to give you guys the opportunity, some other rare opportunity, to work with data that's been collected from very, very rare groups of amnesia patients who who have damage to the hippocampus, who have memory impairments, and who have had EEG recorded from at the scalp. Okay? And you can form your own hypotheses to test in that data. It's pretty cool. Some of the rarest patients around. So you guys have access to that data. So you can test questions from this model. What is the role of hippocampus in recollection or familiarity? Now, that's really, really cool stuff, I think. Okay, and you guys are going to be able to get your hands wet, hands dirty, and get into that data in the nitty-gritty. Okay, so be thinking about, as we move through the quarter, what are some hypotheses and questions that you could test? Okay, and I'm going to help show you some of the ways that you can test them and think about testing. Now, earlier, Fitcher, you said we could test different types of give people different tasks, right? So you could give people tasks for their memory for items. You could also give memory tests for their memory for context, right? And you could see how well people remember the items within the context. So one way that we'll talk about this a lot in class, okay, is you can do, basically, you can give someone, let's say you ask them to study a bunch of words, okay? So if we're interested in how the brain works in cognition, it's memory and learning, okay? First you gotta have to, before you can test their memory, they gotta learn something first, right? So remember we have encoding and retrieval, okay? So let's just start during, you have a study phase, okay? And maybe they learn a bunch of words on a screen, okay? And that screen progression moves, let's say this way. So word 1, word 2, word 3, etc. And let's say you could even update it to say, instead of word, let's say that one word is tree. Okay? The next word is, I don't know, plane. It's another word. Taco. Whatever, right? They learn one word at a time. So we want to keep it real simple in experiments so that we hold all of our other variables constant. And then you want to give them a test, right? So we studied the syllabus. Later on we'll have a test on the syllabus, right? Super simple. Now you show them something else. Let's say we show them that word plane. Okay? Now this is actually an old word, right? Because it came from the prior episode of learning, right? Everybody on board? Okay. Now, let's say, how many of you guys have done SONA credits and participated in research, right? How many of you guys thought it was the best time you ever had in life? Yeah, you almost said it. I know you're interesting. But sometimes they get a little boring, right? So sometimes maybe you tried to sneak your way through it and just kept hitting the key, be like, yeah, I got it, right? Just get your points and get home. So what do you do if your research subject starts doing that to you and screwing with your experiment? How do you account for them just saying, oh yes, that's an old word, and just hitting yes, 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 yes? How do you know if they actually remember it? A dummy question, exactly. Remind me your name?
Karina.
Karina, great job. So a dummy question. What would be a dummy question? To keep them honest? Yeah.
Probably don't answer this question.
Okay, so don't answer this question. You could ask them that, so they just look at something but don't respond. Okay, so that's a good idea. You can ask them to withhold their response. So what we tend to do in the memory experiments is something very much along those lines. You don't just ask them old items. You put some foils in there, some lures, like a fishing lure, where you want them to bite. So you hook them, right? Okay, so we call them lures or foils, but really what they are is new words. So you also have, let's say, a word like clock. Now, the clock is actually a new word, because it never went, or never came from, our study list. So what that does is it holds them honest. That way, if you look at the new words and they keep saying, yup, 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 I remember that, you know that they're absolutely full of crap. And they're lying to you. which means you take all that data you just collected from that person and you put it in the trash can because they just wasted your time. So this is a very important piece of information. This is new items. This keeps them honest. And you tell them, look, there's going to be new items mixed in. There's going to be old items mixed in. And now you ask them to tell you on each one, is this an old item or is this a new item? New or old? So now we're building an experiment. Do you guys see? Now remember, the suggestion was that we do neuroimaging during this cognitive task, right? Remind me your name again? Nayeli. Nayeli said one way we can test hypotheses about the brain activity and whether recollection, familiarity are separate types of brain processes are to actually measure neuroimaging and brain activity during what Vitria said of giving different cognitive tasks to measure these different types of information. So, while we are recording brain activity, we're asking them, do you remember this information? Is it old or is it new? Is it old or is it new? And this allows us to get a measurement of if they're being accurate and honest in their memory. Okay? Now, what we can do is we can categorize responses. Okay? Now, I'm going to make a little box here. Okay? You could have some type of information where, let's just say that this is what the information is, okay? Or what you might call its status. It could either be old or it could be new. You guys follow that? Duh, right? Very simple. Everybody on board? Okay. Now, two other options exist here of what can happen in the experiment, which is what the person tells you. They can either say old or they could say new, right? Okay, so here we're going to say this is what they say, right? They could say old. Actually, I'm going to make it lowercase versus, see how these are capitalized? Little old, or they could also call it new. So see how we have these four options now? These are going to give us tools that we're going to work with in the quarter, because we'll be able to characterize brain activity for these different types of cognitive conditions to allow us to see how the brain activity differs or is the same. Okay? So, they could be right or they could be wrong. How many of you guys have been wrong before? Once? Twice? I was wrong once. I think it was in 98. But it turns out, well, I was mistaken about it. What's wrong about me? You guys never heard that joke? Okay. Okay. So, point is, we can be wrong, we can be right. Let's say that the information really is old, and it really is and they say that it's old. That means they're correct, right? We're going to say they hit the target. So we're going to call it a hit. Okay? Now, again, let's say that the information really is old, but instead they say new. And they say, no, I don't remember that. That wasn't from before. That's not an old item. I don't remember seeing that at all, right? Hey, crap happens. We forget. Right? We miss stuff. So, if it's really an old item and they got it wrong and they said it was new instead, what could be a word that you call that to characterize that condition if they miss it? A miss. That's exactly what we'll call it. Okay. Now, let's say the information really was new. Now, let's start again by saying that they're correct when they do the task correctly, which means it's a new item and they actually call it new. And they're correct about it, right? Okay, so we're going to say that that's correct. But they're correctly rejecting the new information, right? Because they're saying, you're not going to trick me. You're not going to get me to call that old. Get that out of here. They're rejecting it. So we call that condition a correct rejection. Everybody good? Okay. Now, can somebody tell me what you would call this condition and what happens here? Okay, it could be a type 1 error. What would you call that in this situation? Or could you? So first of all, what happened here? So you know how I explained these 4 quadrants? I said, well, it really was this condition and they got it right or they got it wrong. Yeah, Natalie? An incorrect what? Incorrect acceptance. Yeah, okay. So what you guys are both right. Type 1, incorrect acceptance. What we'll call it here is a false alarm. Because it really is a new item. And they go, oh, it's old. I got it. So it's like pulling a fire alarm on a false alarm. You know what I'm saying? We call that a false alarm. Everybody runs out the building. Everybody's all cranky and mad and whatever. So in the memory studies, we call that a false alarm. Okay? Now, this is going to give us a good framework, because now it tells us things that we can design an experiment to test. Make sense? And we'll find out, as you explore in the data, that the brain activity will indeed differentiate between these. Which goes back to the very original question I asked you of, how do you even know that the unconscious mind exists? Because there is a null hypothesis here, right? Why should the brain differ for any of this at all? Right? There's an unspoken null hypothesis that's always being tested and assessed, which is that the brain is inert. The brain is not going to distinguish at the level of neurophysiology this types of cognition. That cognition is separate from biology. It's kind of that underlying null, right? And we're going to find that we can very confidently end up rejecting that null. Okay? So, let's see here. If you wanted to measure brain activity for good memory, which of these conditions would you contrast? Yes.
Number of hits, number of words they remembered was old, recalled correctly was old, versus number they said was not. Whether they said was old before.
So, use the names that we just defined. Yeah.
Hit, incorrect rejection, and missing false alarm.
Yeah, so we would do, let's say, exactly. So you could do it's versus, I'm going to abbreviate correct rejections as CR. Does that work for everyone? Okay? So this might be your explicit memory. Hits versus correct rejections. So if we're measuring brain activity, we're going to see, does the brain activity differ for hits compared to correct rejections? Now, why would this be a good way to test this? Why is that a correct answer?
Well, you're comparing the explicit versus the implicit memory.
Not implicit yet. No,
Implicit.
they are not comparing implicit memory yet. What you're comparing here is you're comparing, obviously, the times you got the memory correct to times when you got it wrong. But this you got it wrong too on false alarm. But why aren't we comparing hits to false alarms? It's kind of a tricky question. So the answer is here. And it's kind of wonky. Okay? It's a little nerdy. But the idea is such that the reason it's useful to compare hits to correct rejections for just a basic memory comparison, okay, is because the comparison allows us to hold constant the factor of being correct. not only is it different based on actually having seen something before and not, right? So experience differs, which is the basis for memory, but experience is different for these two as well. But if you saw a difference between hits and false alarms, and you go to drop the mic at the bar and be like, yo, this is what I found, this is what it's it. Done. Some hater at the bar is going to come back, and they should come back, and say, contraire, mon frère, I don't think so. It's possible that you could have found a difference due to memory, but those conditions, hits versus false alarms, they also differ not just on the factor of memory, but on the factor of being correct. Correctness. Just like the wonky, nerdy factor thing that I mentioned. Okay. However, they were accurate in both times. Here, so it allows you to have a much stronger conclusion as an experimenter about what you're deducing about memory. Is that clear? You guys follow what I'm talking about here? Why is that a useful measure for explicit memory? Can anybody kind of like retell that back to me? Just let me know that you're picking up what I'm laying down. Yes, Fisher?
So like, okay, so if they're looking at a card, for instance, and that it was an old word, and they recognize that it's an old word, obviously they got that correct. And also at the same time, if they recognize that the new word is a new word, then they're remembering what the old word was, and that they're able to recall that that word wasn't there.
Yeah,
Right.
although that's basically what we call recall to reject. It's a slightly different thing, but the idea that's important is just that the correctness is held constant. So anything that differs between conditions can't be attributed to that. So you guys remember in research methods, our job as scientists is we want to isolate that one thing that the conditions are different upon, right? We want to keep every single really tiny little insane thing the same, right? That's what we're doing here, and that's why that's a useful measure, because it keeps all those little tiny trivial stuff the same. Now, let's say you want to measure the unconscious mind, unconscious memory. Which two conditions here would you compare? Or could you?
I would say the same thing.
You could say the same thing, but you wouldn't want to do that. You wouldn't want to compare those. Because you can't, there's no way scientifically or experimentally that you could convince someone that you've excluded the contribution of conscious memory to that comparison. Because they consciously gave you a hit. And so you can't hold that factor constant, unfortunately. What else? Yes? Yeah. Okay, so you could compare, what did you say, misses to false alarms. Yeah, so in both cases, they made a mistake. Okay, so now we're getting a lot closer. So if we want to study unconscious memory, unconscious mind, you can compare times when they made a mistake. However, that also does not hold constant the consciousness factor. It allows us to study, actually, the different form of memory in that regard, that you're actually holding that difference. So they think they're right, but they're wrong in both cases. What would be a better way to tap into the non-conscious? Yes?
I would say hit and miss because maybe unconscious is more related to old material.
Indeed. So hit and miss is getting closer. Okay, but again, the hit factor and the miss factor changes the conscious awareness. Because they experience both conditions. It's both an old item. But this they consciously remember, and this they consciously forgot. So you can't actually, they don't actually differ unconscious. So here's the trick. Okay? You want to study implicit memory instead. Okay? What you're going to study miss versus correct rejections. Okay, now the reasoning, the logic behind that is as follows. Okay? So, what did they say in both of these conditions? What did they tell you verbally? Did they tell you that they remembered the information from the past? They did. When you say miss, are you telling the experimenter that you remember something? No, because you called it new. Right? So look. We're just comparing these two conditions, right? This is what they said. So in both cases, this and this, right? They said the exact same thing. They said, I think that's new. I've never seen that before in this experiment. You guys follow? But how do the conditions differ?
One they were correct, one they were wrong.
Yeah. They're telling you the same thing, but one time they're right and the other time they're wrong. So, how does this allow us to tap into implicit memory? Well, very elegantly. Okay? And the idea is that, I'm going to erase that there so it doesn't get confusing, but in both of these situations, okay, they have told you the exact same report about their conscious awareness. Their conscious mental access to that memory is identical, isn't it? Because it's null. They're saying, I got nothing both times. I have no conscious awareness in this time, and I have no conscious recollection in this time. However, we know, because we controlled the experiment, that in one of these conditions, they actually did experience it before, right? And the other one we know is new. And so they did not experience it before. Therefore, any place where the brain activity differs, can we attribute it to a conscious awareness? No. Because their consciousness, their conscious awareness of their memory is the same. It's a lack of a conscious awareness because they got nothing. However, anywhere where those biological patterns in Nayeli's fMRI experiment, anywhere where those biological patterns differ, it can only be attributed to the factor of one of those conditions having been experienced before, and the other one not. Because that's the only dimension by which they differ on. You guys follow the logic? Therefore, what we've created is a measurement in which we can see brain biology remembering something in the past that the mind has consciously forgotten. Question?
Yeah. Okay, much as I hypothetically speaking, this was, it worked out.
Yeah.
My question about the miss is that how can we account for, hypothetically speaking, that participant got primed before the study? Let's say it was the word tree, that word was new,
Yeah.
right? But somewhere they thought it was there just because they were primed right when they walked in.
It's possible they could have read the word tree before they walked into the study, yes. But what we'll learn about is that when we create the brain activity comparisons for these conditions, we average that over hundreds of trials. And it's very unlikely that that one time that they were primed by the word tree is going to drive the effect that's averaged out of 100 things they weren't primed by. So, very good question. But I want to return back to the logic to this and get feedback from you guys to make sure that you understand what we're doing and why we're doing it. Who Who would like me to explain this again in a different way? Okay. So, let's look at it as if we draw some brain activity, okay? So let's say we have pattern of EEG, or ERP, we'll get into that in a minute, and it rises, falls, and it does some funky stuff, and it moves over, okay? And that's in response to a stimulus. Now let's say that stimulus is you know, whatever, these are words, okay? Now, let's say that a hypothesis is that this pattern of brain activity is tracking conscious memory awareness. Okay? Now, if you have two conditions, miss and a correct rejection, okay? Are they the same or different in their conscious memory awareness? They're the same. Why? Somebody in the back, tell me why these are the same in their conscious memory awareness. No, they didn't remember at all. Remember? They forgot.
Well, we're saying correct rejection.
Okay, so they remembered it's not an old word. Or, well, at least, it's not that they remembered it's not an old word. It's that they had no memory that it was an old word. Therefore, it is presumably new because I don't remember it from the past. Right? So these are both have the same reports of whether or not they can consciously remember, right? Mentally. So they said, no, I can't. Because they said new. However, so if the hypothesis is that this traces conscious memory awareness, then these two should be exactly on top of each other, shouldn't they? You guys follow that logic? Make sense? However, what would you say if at some point in time there is this difference between the conditions? What does that mean? What do you interpret from? In the back, what would be your conclusion that you could draw from that? What do you think? Do they differ based on conscious awareness? No. What is the one thing they differ upon? Huh? No, because they're both similarly not consciously aware of that memory. How do these conditions differ? They're the same in what they say, but why aren't they in the same box? They're in different boxes, right? One time they were right and one time they were wrong. Which, about what? About the question of did you experience this in the past? So we know the only dimension that these two factors differ upon is whether or not they were experienced in the past. So what does it mean if the biology signal differs based on whether or not something was experienced in the past or not? What?
I was going to say that the correct response is going to be lower because they have absolutely no recollection of it, and they've never seen it before.
Not quite. Not quite.
Okay.
What it means, if a biological signal differs based on whether or not something was experienced or not before, very, very simply, it just lets you know that that biology is remembering. It remembers something from the past. It's changing based on experience. If your kid gets suspended from school, and he comes home, and you whack him, say, you're in trouble. I'm going to kick your butt. The kid comes back next week, he got suspended from school again for doing the same thing. You're going to say, what's wrong with you? Why didn't you learn? Why didn't you learn from experience, right? Why wasn't there a change based on something experienced before? That's the essence of memory. This is different based only upon the fact that one of these was experienced before, which tells you that the biology is giving you a memory signal, even though that memory signal has not reached our mental conscious awareness for them to report. Does that help to rephrase it in a different way? We'll come back to that over the course of this. Yeah.
I have a question regarding that. For the NIS, with the solid line, why is it smaller than the correct rejection?
That's a very good question. Why is this a smaller dip than this?
Yeah.
Well, it might. So it's a deep question, actually, and there could be a lot of reasons. One, the simple answer is because that's how I drew it, and it was make-believe. The more practical answer is that when we see patterns like this in real data, it can mean that it's not that it's less big. Perhaps this is a greater positivity. This is a bigger negativity. So it could actually it could mean the addition of a component, a subtraction of a component. It's basically complicated. But just bigger or more activity doesn't mean necessarily better or worse. It just means different. Okay, so that's a really good question and a really good point to kind of segue on. And we can talk about some elements of EEG. Okay, because now we've so just to come up for air. Okay, we've introduced a model of understanding a little bit about memory. We talked about testing items. You can also test context by asking for people, what's the context that that thing came in? What was the source of that information? Okay, so you could ask them this, and then you could also ask them another question about it that moves forward. Let's say the word stays on this, and you ask them, did you see the word plane at LAX or at San Francisco Airport? LAX or SFO? You're asking for their source of the memory. Where did you see that word airplane? You guys follow the logic? And so the idea is that if they get the source memory correct, it's reflecting that they're remembering the context. If they just get what we call the item memory versus source memory, the item memory is going to be reflecting that what, or the familiarity. So we can test that. So we started with this model about how we think that the medial temporal lobe and hippocampus and memory might be operating, I should say. We've looked at some ways that we can design experiments to test that. We can test item memory and we can test source memory. We can also add some wrinkles. Okay? Some wrinkles you could add is a confidence scale. 1, 2, 3, 4, and 5. Like when you go to the doctor's office. How bad is the pain rated on a scale of 1 to 5? You can do that. How strong? Do you remember it really sure or just a little sure? This is really nice to track onto our item familiarity, right? Because sometimes, oh, somebody seems so familiar, where do I know you from? Versus, oh yeah, you know, that person seems a little familiar. But when we recollect really clearly, it's always with, we're pretty confident about it, aren't we? Okay? So now what I've tried to introduce to you are some tools of cognitive psychology. Tools of psychology that we can use to understand and investigate cognition. Okay? So our tools include item memory, it includes source memory, it includes item confidence responses. You can even ask how confident they are that they saw the word plane at San Francisco airport as opposed to LAX, by giving them a confidence scale back here too. These are tools that we will use a lot this class, okay? Because they're going to give you options to develop your hypotheses of what you want to compare when you're analyzing brain activity, okay? Now, we also talked about the tools that we introduced of using behavioral, the response patterns of hits, misses, correct rejections, and false alarms. And we talked about the strategies to use critical thinking to understand how we can gain leverage on different memory conditions based on their response profiles, right? And comparing that to gaining leverage on the conscious mind of explicit memory and the unconscious mind of implicit memory. So we've covered a lot of stuff, right? It might seem kind of simple at first, but you guys see I was building into a pretty complex web, right? We're building a very strong framework from which to launch experimental expeditions into the human mind. That's exciting to me. I hope it is to you guys too. Because that's what we're going to be doing. Okay? Are there questions on those elements before we move forward? You guys feel like you got it down? Okay. So, what I'm going to do is, does anybody need this on the board any longer to write it down? Does anybody want to take a picture of it to upload for your study? Come on up and take a picture of it. Or you know what? I'll take a picture and I'll post it to the site for you. Okay? And then I'm going to erase it and I'll start all over again on something else. Okay? Oh, it's back. Okay. You guys want to do a class selfie? Let's get it right. Okay, so we started off with this model. Okay. Then we went to this. Then we went to this. And then we talked about that. Okay. So, I'll try to add those to the Blackboard or email them out to you guys later. That way you can have them if you want. Sound good? Okay. Okay, start with the next phase. I left that up there because it's our brain activity. We're going to get to that now, okay? So you start off with the human brain. You get your central sulcus, cerebellum, pons, hindbrain, occipital cortex, all that good stuff, right? Now, let's say you rotate that this way, okay? Now we've got a coronal slice, right? Kind of looks like that. You've got your cortical folds on top. Get your ventricles up there. Everybody knows these basic views, right? The question is, how do we figure out what the hell is happening in here, here, and here without drilling a hole? to see. It's really tough, right? You've got to use these complicated measures that are flawed. Things like fMRI, EEG. They're complicated, they're flawed, they're not perfect. They can't do exactly what we want them to do, but they can be helpful to trying to get us to where we want to be in understanding the biological elements of the mind. Okay? So, when we, and of course you guys know that, most of you guys know we have these pyramidal neurons, right? You have the soma, axon, dendrites, all that good stuff. So, they're packed in all over here. Now let's say that you have an electrode. That's there. That electrode has a wire that runs over here, and that wire comes in to your laptop computer. You know, that shows you some electrical traces of what's happening. It's picking up of the neural activity from the brain cells. Okay? Now this is just a brief overview of what hopefully you guys have already covered in EEG. EEG reflects the summed potentials of millions of neurons. Not just one, but this times what Austin Powers would say, 1 million. Okay? Dr. Evil, sorry, in the Austin Powers movie. Times 1 million. Okay? Millions of neurons firing cohesion together. Okay? Network level dynamics. Okay? Because this spot where this electrode is contains just millions of microscopic neurons. And we can record that activity, okay? And it oscillates, and it comes up and down, and it's always moving. That's what EEG activity looks like, okay? So, you have these electrodes. They're situated at different spots on the head. You have the wires come out from them. Okay? The wires are going to come in and they're going to go feeding in to your laptop. You'll see those traces, and you'll type it on your computer pad or whatever. Make sense? So, you have these electrodes, and what they're doing is they're picking up that summed potential from millions of brain cells, working in and firing cohesion together. Because that signal is microscopic in its microvolts. But it's big enough for us to measure as it goes through. And it comes from your cortex. It goes through the meninges, the skull, the scalp, past your hair, a little space of air. And then our electrode picks it up here. So it has to be a pretty big signal for us to still see outside the head. That's why it has to be reflecting millions of neurons firing together. So they sum up and you get a bigger activity. Okay? Now, when we do that, we can measure it in all these electrical traces. Now, a couple things. There are some limitations to the method as we'll use them. Okay? The electrodes at the scalp can only pick up, so see how I put them here? It can only pick up activity at the top of these gyri of neurons at the top. It cannot pick up activity in here. Okay? So, just so you know, when we're looking at this activity, it can only pick up sort of the top of the gyri. Okay? And the reason is because the orientation of these neurons. Okay? They're generally oriented like this. But then the cortex folds, right? And as it folds, these rotate back down. And now they're oriented in a different way, and they start to cancel each other out. when you're at these bottom cell side. Okay? So it's important to know when we look at these patterns of activity, what it is that they represent, so that we're all starting from the same sort of foothold, starting point. Is everybody on board with that idea? Okay, now that's really, really useful. Now, what are some of the biggest advantages that we've already talked about, most of you guys from our previous classes that we shared together, that is some of the biggest advantages of EEG? That is some of the reasons why you would want to do it. Yes, ma'am?
Because it's not invasive, you can do it easily, plus it's expensive.
Absolutely.
And it's also easier to do on kids because it's also not like, it's not gonna scare you.
Absolutely.
Like
So it's cheaper, it's easier to do on kids, it's non-invasive, relatively simple. What's another big advantage of the data that you get from it? Yes, Victor?
It has the temporal resolution.
Yes, temporal resolution. It's going to be like a hallmark of our quarter. Okay? The fact that we can break down neurophysiological activity on the order of milliseconds. Okay? Remember we said earlier at Nayeli's question about different brain areas that we can find active for different types of memory? We also said, what if you find the same area is active at different times? Okay? You're gonna learn how to work with brain data and find that the same electrode can show a different effect for different types of memory at different times because it's such a sensitive measure for temporal precision and temporal resolution. It's fantastic. Okay? So, we're going to see that that's one advantage. Now, one of the disadvantages of this technique is that all we can say about the spatial location of this information is that it comes from this spot on the scalp. Okay? It comes from this general area on the scalp. But that general area contains millions of neurons, so that really kind of means crap for us. It's like, how many of you guys have been like traveling other places and they're like, where are you from? And you have to tell them you're from LA. Because if they ask, well, you're from
Rancho Cucamonga, they all look at you like,
Yeah.
where are you, like, is that even a place? That's
Oh,
not like swear word. Like,
exactly, yeah, you're from Rancho Cucamonga, or you're from Colton, or you're from Yucaipa, right? People look at you like, what the heck does that mean, right? So you have to expand your geography, right? And all we know from this trace is that the location-wise is they just come from this broad geographic area. Okay? It doesn't tell us that they came from this street address in San Bernardino. Because people will know that. They're like, oh, you're just from Southern California, whatever. But if you get labeled as someone from Southern California, there's some stereotypes that people might jump to, right? Southern California has a couple stereotypes, right? Every area of the country has some, right? Everyone's a little different, right? We have our own down here, right? Some of them are kind of funny, some of them aren't, right? But would that be a fair stereotype to levy upon you just by knowing that you're from the broad Southern California, LA area? No. Would that be accurate? Maybe, but probably not. Because there are millions of us here, just like there are millions of neurons in here. And so if all we know is, oh, it comes from this broad area, it's not very helpful to us in spatial resolution of dialing in these effects to a location, because there's actually a lot of stuff within it that could vary. Or you could be from Cucamonga, you could be from Yucaipa, you could be from Redlands, San Bernardino, whatever. Okay? So, temporal precision is very good. Spatial precision, not very good. In fact, it gets worse. Okay? How many of you guys have heard of the inverse problem? Yeah, this is going to be an important part to remember through the course too. Okay? When you find your discoveries in our data, when you make your discoveries in your testing hypotheses with EEG, okay, you are not going to be able to say where in the brain, underneath that cortical or underneath that scalp area, that effect was actually generated by. And the reason is because of what's called the inverse problem. Okay? Now the inverse problem says that, and it's basically, it's a straight up mathematical problem of physics. And it says that if all you know is where this spot is on the head or on the scalp, it is impossible to know with certainty what subcortical area in other areas of the brain led to creating that pattern of neural activity. And the reason is because there is an infinite number of sources of brain activity that could possibly be contributing to any given pattern at the scalp. So what it says is that it's impossible to know what the internal neural generators are of an effect that we see at EEG at the scalp. You just can't do it. It's an infinite number of possibilities mathematically. Okay? Now you can do the opposite. If I tell you that there's neurons that are active here, we can come up with a pretty good mathematical approximation based on the connectivity and the axons and where they project to at the cortex to know where that connectivity is likely to go here. That's called the forward solution. But the problem for us is called the inverse problem. You can't work backwards. You can't take a pattern of effects like this and say that it comes from an electrode at this site. You can't take a wire, run that wire out, and give that pattern of activity from this spot. You can't say where, deeper in the brain, this pattern you see at the scalp is from. You just can't do it. And that's okay. You just can't do it. I mean, you know, whatever. Like, I like to fly airplanes, but I can't fly my car. It's okay. Car's good for driving. Can't take a plane on the road. Do different things for different purposes. Okay? So, we know that we can measure time very well. And this goes over long periods of time or short periods of time. This is the kind of data we'll get from millions of neurons. Everybody good? Yeah? Okay. So, let's see here. This thing. How do we move? So first of all, here's a question for you guys. Hopefully you guys remember this from previous classes. What's the difference between this trace here and, say, this trace here? Is there different names you would give them? Yes?
About like dopamine.
Almost. It's not quite what I'm thinking about, though, this time around. So all very simply is that this is basically, this is a core part of the course. Of course, this is called EEG. Okay? EEG stands for electroencephalogram. Electro, because obviously we're recording electroactivity. Encephalo is Greek for brain, and gram, of course, for measuring something. Okay, so it's just a measurement of electrical brain activity. Now, this is a raw trace. It's very messy. It's crazy looking. Okay, we're going to see that in the data when we work with it. Okay, now, what we will also see is we're going to work with that data. I'm going to teach you how to work with it such that you can derive results, not from this messy, noisy data, but we're going to average out the noise from hundreds of trials. Remember we talked about that earlier? How do you know it's not this one thing? Well, you average it over hundreds. It's probably not that one thing. Okay? To create something that's much cleaner looking of an electrical potential. Okay, so this is called, essentially what's called an event-related potential, or ERP. A core component of the class. It's the title of Dr. Stephen Luck's book that we are following. The event-related potential technique. And that's what we are here for. We will use this technique of taking event-related potentials to study the brain activity, okay, happening from millions of neurons during different cognitive events. Okay? That we can control, such as showing them items that they might remember versus sources or contexts that they might remember. So we can control item memory or source memory and confidence ratings to categorize and cut and slice apart. So let's say you can take a time point here. At this time point, they saw something that they remembered with a hit. And this other time point, they saw something that was correctly rejected. And at this other time point, they saw something that was a false alarm. And at this other time point, they saw something that was a miss. Okay? So what you can do is you can create windows around that brain activity when that happens. And we slice and dice the data. We categorize it based upon how they responded with their confidence of how strong that memory was for the item or for the source. We can categorize whether it was a hit, a miss, a correct rejection, or a false alarm. And then we can average hundreds of those things together into an electrical potential that is related to that particular event of a hit. We kind of bring that together for everyone. Does that help to kind of fill in some gaps that we started with? Yes, ma'am.
Like when they do EEG on people who have seizures, it's like when they take that little chunk of like the thought in the brain and they kind of get a seizure.
It's not quite like the clinical work with the seizures, because that's more about just analyzing, quantifying the peaks and troughs of the EEG. But this is more about like non-clinical seizure work, where we're gonna cut this apart and to average it. And so let's say that we have 300 trials in a memory experiment, right? Throw me a random number out of 300 that you think would make sense for how many times they have hits.
120.
120, perfect. Okay, 120 hits. How many times out of 300 minus the 120 that's already taken out might there be correct rejections? 50, perfect. Okay? Okay, so what we'll do is you'll see that you'll average this activity of the 50 different of those and the 120 different of these, and all this crazy noise will average out to some really nice, soft, smooth lines. And then what we'll do is we'll measure anywhere where these activities differ between conditions. Okay? So this is going to give you a value, let's say, +5, and this is going to give you a value, let's say, -5. Okay? And we can graph that then, okay, on our graph of +5 and -5. And -5, right? Put error bars on there, and then you can run a statistical test, as you guys are all experts on, right? To measure the difference of whether or not this is actually statistically significant. And that will give us our results. And we're going to learn how to use software to do that for us. Because we have to use software to be able to categorize and work with all these inner workings and physiology related to the inside of our skull. All in ones and zeros. It's pretty cool. Okay? And so we'll use those stats, because everyone here has stats, right? And so we'll do that at the end to compare these different patterns of measure the amplitude of these different effects during different windows of different times. So let's say this is let's say this is 400 milliseconds, and this could be 600 milliseconds. Okay? And this is time point 0. So moving forward in time from 400 to 600, we see that the amplitudes differ for one condition relative to another. Misses versus correct rejection. And we can see then some insight into how there's a biological signal for memory of past experience that's differing at a certain place on the scalp between a certain point in time that was not even available to conscious awareness. How do you guys feel about that? Is that a lot? Yeah, it's kind of... Okay, why don't we take five minutes, take another break, okay? Digest this a little bit, think it through, all right? And we'll come back and revisit and finish up. Sound like a good plan? Okay, cool.